Welcome to my 73rd tutoring session in A-level chemistry. In this video, I'll explain the IR spectral characterization of alkanes, alkenes, and alkynes. Later in the video, I will discuss the IR spectral peaks of CH bond formed by sp3, sp2, and sp hybridized carbon. Now, hydrocarbons are organic compounds that contain both hydrogen atom as well as carbon atom. And you will find the presence of carbon-carbon as well as carbon-hydrogen covalent bonds in hydrocarbons. Hydrocarbons basically are of three types: alkanes, alkenes, and alkynes. Now, alkanes are saturated hydrocarbons characterized by the presence of carbon-carbon single bond in their molecule. And the carbon atom in alkanes is sp3 hybridized. While alkenes are unsaturated hydrocarbons characterized by the presence of carbon-carbon double bond in their molecule. And the carbon atom in case of alkenes are sp2 hybridized. And alkynes, they are highly unsaturated hydrocarbons characterized by the presence of carbon-carbon triple bond in their molecules. And the carbon atom in case of alkynes, they are sp hybridized. Now, the carbon-carbon triple bond is stronger than the carbon-carbon double bond, and in turn, the carbon-carbon double bond is more stronger than the carbon-carbon single bond. So, as the bond strength increases, the absorption value also increases. That is to say, it takes more energy or a larger wave number to stretch a stronger bond. Stronger the bond, more energy required to stretch that particular bond. Now, that is about the carbon-carbon bonds. Now, talking about the carbon-hydrogen bonds in alkanes, alkenes, and alkynes. Now, to begin with alkanes. Now, the CH bond in case of alkanes, it is formed by overlap of an sp3 orbital from carbon and s orbital from the hydrogen atom. So, a carbon-hydrogen covalent bond is formed by mutual sharing of pair of electrons. That is how the CH bond is formed. So, CH bond in case of alkanes, it is formed by overlap of sp3 orbital from the carbon and s orbital from the hydrogen. In case of alkenes, the CH bond is formed by overlap of an sp2 orbital from carbon and s orbital from hydrogen. While in case of alkynes, the CH bond is formed by overlap of sp orbital from carbon and s orbital from the hydrogen atom. So the CH bond in case of alkyne is more stronger than the CH bond in case of alkene, and in turn the CH bond in case of alkene is more stronger than CH bond in case of alkane. And this is reflected by the respective absorption values where the stretchings of these bonds occur. So in case of alkyne CH bond, the absorption occurs somewhere around 3300 to 3320 centimeter inverse as compared to that of alkenes with wave number of 3000 to 3100 centimeter inverse. This is because the CH bond in case of alkynes is stronger than the CH bonds in case of alkenes. So the weakest bond or the weakest CH bond, you find it in case of alkenes. So why the variation in the strengths between the carbon-carbon bonds and the CH bonds? Let's find out. So it's better to brush up some of the basic concepts in organic chemistry before I explain the concepts. Now, hydrogen is the first element in the periodic table with atomic number 1, and the electronic configuration of hydrogen is 1s1. It has a central nucleus that contains positively charged proton with only one electron in the s orbital orbiting around the nucleus in its respective shell or energy level. So there is only one shell in case of hydrogen atom, which is also the valence shell. And in case of carbon, electronic configuration of carbon is 1s2, 2s2, 2p2. So you find 6 protons in the nucleus of carbon atom, 2 electrons in the 1s orbital. So this is present in the first shell, and 2 electrons present in the s and the p orbital in the second shell, which is the outermost valence shell in case of carbon. So these electrons, be it s electron or p electron, it orbits around the nucleus in its respective shell or energy level. Now in case of carbon, where you find 6 protons in the nucleus, the nearest orbital is the 1s orbital. This is followed by the 2s orbital and the 2p orbitals. And in case of 2p orbitals, they are oriented along the x, y and z axis. The px orbital is oriented along the x axis, while the py orbital is oriented along the y axis, while the pz orbital is oriented along the z axis. So when you compare and contrast all these different types of orbitals, you will find that the s orbital is more closer to the nucleus of the atom than the p orbitals. And therefore, because of the close proximity of the 1s orbital, the 1s electrons will be strongly attracted towards the positively charged protons present in the nucleus of carbon atom. So the key takeaway is that attraction of 1s electron towards the positively charged proton present in the nucleus is more as compared to that of 2p electrons. So this basic information will help you in understanding the characterization of IR spectra of alkanes, alkenes and alkynes. Now the triple bond is stronger than the double bond is stronger than the single bond. So as the strength of the bond increases, a greater wave number is required, or a greater frequency of IR radiation is required to induce the vibrational frequency or the stretching vibrations in these bonds. So as the strength of bond increases, the energy of IR radiation, that is the wave number, also increases. Now as you move from sp3 hybridized carbon towards the sp hybridized carbon, you will find that the polarity of the CH bond increases. That is to say, the CH bond in case of alkyne is more polar than the CH bond in case of alkane. And therefore, the CH bond strength in case of alkyne will be much more than the CH bond strength of alkane. So this all because of the hybridization of that particular carbon atom. So in case of alkane, you'll find that the carbon atom is sp3 hybridized, while in case of alkene, the carbon atom is sp2 hybridized, while in case of alkyne, the carbon atom is sp hybridized. So as you move from the sp3 hybridized carbon in alkane towards the sp hybridized carbon in alkynes, you'll find that the S character is increasing. So 25% S character in case of alkenes, 50% S character in case of alkenes, and 75% S character in case of alkynes. As I've already explained, more the S character, closer will be the S orbital and the S electron towards the nucleus. And as the S character increases, the S electron will be more closer to the nucleus, and thereby there will be a strong attraction between the S electron and the positively charged protons present in the nucleus of the carbon atom. And this strong hold of the electrons by the positively charged protons of the sp hybridized carbon results in a stronger bond. So more the S character, stronger will be the bond, because remember, the S orbital is more closer to the nucleus as compared to the p orbital. So more the S character, strongly will be the electron drawn towards the positively charged protons present in the nucleus of carbon atom, making the bond stronger. And therefore, the CH bond in case of alkyne is more stronger than CH bond in case of alkene and alkene, because of difference in their hybridization. So an S orbital is closer to the nucleus than a p orbital. Therefore, carbon-hydrogen bond formed by sp hybridized carbon is shorter and stronger than carbon-hydrogen bond formed by sp2 hybridized carbon, which is in turn shorter and stronger than a carbon-hydrogen bond formed by an sp3 hybridized carbon. So shorter bonds are always stronger in nature. So why it is shorter? Because the strong attraction between the positively charged protons present in the nucleus and the electrons of the hydrogen atom. So there is only one electron in the hydrogen atom, and that electron will be attracted more towards the nucleus of the carbon atom. So increasing S character shortens the bonds, and thus bond strength increase with increasing S character. And that is why the CH bond in case of alkyne has a high dipole moment, that is to say it is more polar as compared to that of CH bond in case of alkene and alkane. So what you find here is increase in polarity. So initially there is increase in the polarity of the CH bond because of the hybridization, that is variation in the S character, and ultimately end result is that the CH bond strength increases with change in the hybridization of the carbon atom. So in case of alkyne, the bond angle is around 180 degrees between the triple bond and the CH bond, and therefore the nucleus of the hydrogen atom is in line with the nucleus of the carbon atom, and therefore there is strong attraction of the shared pair of electrons between the carbon and the hydrogen atom towards the nucleus of the carbon atom, and therefore increasing the polarity as well as the strength of the bond. So that is with respect to the CH bond. Now coming to the carbon-carbon bond, in case of alkynes, the distance is 1.2 angstroms, while in case of alkenes, distance is 1.33 angstroms, while in case of alkane, the carbon-carbon distance is 1.54 angstroms. So a shorter bond is always a stronger bond. And that is why the order of bond strength is as represented here. So the CC bond as well as the CH bond strength will be in the same order. And hence their absorption values will be in that particular order in the IR spectra, which I will be explaining later in the video. So stronger bonds are difficult to stretch and therefore require greater energy or a higher frequency of IR radiation. So I'll explain the IR spectral characterization of alkanes, alkenes and alkynes, employing the IR spectra of 1 octane, 1 octene and 1 octane as representative examples. So here, I'll be making use of IR spectra of 1 octane and 1 octene. So the triple bond is more stronger than double bond, which is in turn more stronger than the carbon-carbon single bond. So let me draw a reference line here so as to separate the fingerprint region from the functional group region. Now the fingerprint region is also considered as the single bond region because most of the absorptions due to carbon-carbon stretching appears in this fingerprint region because the carbon-carbon bonds are weaker as compared to the carbon-carbon double bond. So absorptions due to single bond stretches appear in the single bond region as they are weaker bonds. Now these values range or it varies depending on the structure of the molecule. Now in case of 1 octane, I mentioned the value as 1200 centimeter inverse. This is only an average value that I mentioned here, but the values may vary. It may vary depending on the structure of the molecule. And also how far the neighboring functional groups are influencing this carbon-carbon, that is the strength of this carbon-carbon single bond. Now in the double bond region, absorptions due to double bond stretches results in a sharp peak in case of 1 octane, and the absorption due to carbon-carbon double bond stretch is seen at around 1642 centimeter inverse. So octane is an alkene, so you will not see any peaks for the triple bonds because there are no triple bonds in the alkenes, and hence there will be no peaks in the triple bond region. Now coming to the IR spectra of 1 octane. So you'll see a sharp peak at around 2159 centimeter inverse, and this peak is due to triple bond stretch. Now triple bond, as you know, it is a stronger bond. This carbon-carbon triple bond is a stronger bond, and absorption due to this strong triple bond stretch occurs in the triple bond region. So it occurs at a higher wave number. So more energy is required to stretch the carbon-carbon triple bond, and hence a higher wave number is required, and hence you see a peak at a higher wave number. And there are no peaks in the double bond region because there are no double bonds in alkynes. And that is why you don't see any peaks in the double bond region. So this is the order of the absorptions for carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. So as the bond strength increases, more energy of the IR radiation is required to bring about their respective stretchings. So stronger the bond, peaks appear at a higher wave number because more energy is required to bring about stretching of the particular bonds. Now coming to the CH stretching bands of alkanes, alkenes and alkynes. Now again here I will be making use of higher spectra of 1 octane and 1 octene as representative examples. Now remember, peaks in the IR spectra, they appear due to absorption of IR radiation by different bonds and functional groups at specific frequencies. Now let me draw a reference line exactly at wave number of 3000. Now why I have drawn a reference line exactly at 3000 centimeter inverse is because the CH bonds in case of alkanes or the alkyl CH stretching occur lower than 3000 centimeter inverse, while the CH stretching for alkenes and alkynes, they occur at wave number higher than 3000. That is why it is always better to draw a reference line at 3000 centimeter inverse. You can say it is a kind of differentiating line. So in case of 1 octane, the CH stretching bands of hydrogen attached to the sp3 hybridized carbon atoms occur at lower frequencies, somewhere around 28572 to 2998 centimeter inverse. And here the carbon atom is sp3 hybridized. And likewise in case of 1 octane, you find the CH stretching bands of hydrogens attached to sp hybridized carbon atoms occurring at lower frequency. Now both in case of octene and octane, apart from the double bond and triple bond, there are presence of methylene groups, that is CH2 groups. Around 4 to 5 CH2 groups are present. And these CH stretching bands that are sp3 hybridized are because of these methylene groups. And CH stretching bands of hydrogens attached to sp2 hybridized carbon atoms, they occur at a little bit higher frequency as expected because the carbon atom is sp2 hybridized. So CH stretching bands of hydrogens attached to sp2 hybridized carbon, they occur at a higher frequency. While the CH stretching bands of hydrogens attached to sp hybridized carbon atoms, in case of alkynes, they occur at a higher frequency as expected because the carbon atom in case of alkyne is sp hybridized. And I've already explained the importance of hybridization of these carbon atoms. So it is the hybridization of these carbon atoms which decides the stretching frequency of either the carbon-carbon bond or the carbon-hydrogen bond. Now in case of alkynes, why the peaks appear at a higher frequency? That is because the electrons involved in the formation of CH bond, they are more strongly attracted to the carbon nucleus as observed in the structure. And this stronger hold of the electrons by the positively charged protons of the carbon atom enhances the strength and stability of the bond within these class of compounds, that is alkynes. And therefore, their polarity and the strength of the bond increases. And you can see the shift in the CS stretching. So the shift in the CS stretching for alkynes is more as compared to that of alkenes. This is because alkynes, the carbon atom is sp hybridized, while the carbon atom in case of alkene is sp2 hybridized. So the CS stretching bands is in the following order, because the CH bond in case of alkyne is more polar and hence more strong as compared to that of less polar CH bond in case of alkenes and alkanes. So the CH bond in case of alkyne is more polar and more stronger as compared to the CH bonds in alkenes and alkanes. So that is why you see a peak, a strong and sharp peak for the CH bond in case of alkyne at a higher frequency or a higher wave number. Now one spectra that is left out to be explained is that of octane. So in case of octane, you don't find any unsaturation, because octane is a saturated hydrocarbon. It is completely saturated hydrocarbon where you find the presence of only carbon-carbon and carbon-hydrogen covalent bonds. So a partition line at around 3000 centimeter inverse, and you see stretching frequency for the CH bands. So CH stretching bands for the octane is around 2867 to 2969 centimeter inverse. So you can see this value is coming close to 3000, but it is not exceeding 3000. So that is why it is recommended to draw a reference line at around 3000. For alkanes, it will be less than 3000, and for alkenes and alkynes, it will be more than 3000 centimeter inverse. So even in case of octane, you will find the CS stretching bands at around 2857 to 2998 centimeter inverse. And the CS stretching bands for the CH bond formed by sp2 hybridized carbon is seen at around 3079 centimeter inverse. And in case of octane, there are no CH stretching peaks due to absence of CH bonds formed by sp2 hybridized carbon in alkenes. And therefore you see only CS stretching peaks less than 3000 centimeter inverse. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.